This is your 5.3 notes. Exponential log equations. So in this section, we're going to be solving equations that have an x in the exponent or x inside a log function. Alright, now the first type we're going to look at is exponential equations, and we're going to use log forms to solve them. So to solve an exponential equation using log forms, you do these 4 steps. Okay, it's going to invite isolating the exponent part by itself, and then dividing whatever we need to get it isolated, and then change to a log form. So to give you an example, just to start off, and then we'll just come back and look at this as we walk through it. We want to solve this equation, right, for t by converting it to a log form. And then after we're done, we're going to solve it graphically just to make sure that we are getting the right answer. So notice the first thing this tells us to do is rewrite the equation with the term containing the exponent by itself on one side. So what that means is this is the term that contains the exponent, just the 10 to the 4t power. Okay, so what that first bit of information is telling me is I need to take this 150 that's being multiplied by the 10 to the 4t power, and I need to divide it away. So I need to get rid of this 150 off the bat. That's what step 1 is telling me. Alright, so now I have just the 10 to the 4t by itself over here. Alright, and then over here on this side, alright, this 0 cancels this 0. 15 goes into 30 2 times, and then there's that extra 0. Alright, so this is 20 equals 10 to the 14. Now, what you got to remember, do not divide by 10. This is not multiplication. This is an exponent. Okay, we cannot get rid of this 10 by dividing by 10. Okay, so we have to, when we're solving and the t's in the exponent, we have to bring in logs of some sort. Now, this says change the new equation to the log form. I do it a little bit differently than that. What I say is at this step, instead of changing it into log form, I say my step is bring in the logs. And what I mean by that is that if two things are equal to begin with, right? So if I have, what I'm basically saying is if A equals B, then the log of A equals the log of B. Alright, and just to kind of give you an illustration that this is perfectly fine. Like if I had the log of 5, right, and hit enter. Alright, oops, and I also have the log of 3 plus 2. Okay, 3 plus 2 is 5. So since 3 plus 2 is 5, the log of 5 and the log of 3 plus 2 should give me the same thing. That's what I'm trying to say here. If the two things are equal, then they're going to have the same logs when we put them into the log function. So if these two things are equal, then what I'm saying is, since 20 equals 10 to the 4t, then the log of 20 should equal the log of 10 to the 4t. Right? So the idea is, since these two things are the same thing, they're going to produce the same output when we put them into the log, because they were the same thing to begin with. Alright, now, this is a property we talked about in the last section. This is log without a base, it's understood to be the base 10 log. Right, and when this number down here and this number here agree, remember the log and the exponential things, they wipe each other out. So what we're left with over here is just the 4t. Right, these wipe each other out, and we're left with just that 4t, and then over here we have the log of 20. Right, and then divide by 4 on both sides, and we get t equals exactly the log of 20 over 4. and then you go to your calculator to get a good approximation. So log of 20, close parentheses, divided by 4 gives me 0.325 to 3 decimal places. So t is approximately 0.325. Alright, and then part B says solve the equation graphically to confirm the solution. So if I want to do it graphically, if I want to do it, remember, left side of your equation goes into y1, the right side of your equation goes into y2. Right? Now I'm going to have to adjust my window, and now I've got it already set, but notice the reason why I've got it set like this. 10 to the 4t power, right? 10 to as the base to a power grows extremely fast. Okay, and not only are we taking 10 to the 4t power, we're also multiplying it by 150 after that. So this thing is so insanely steep that it'll get up to 3,000 in no time. So notice my window only goes from -1 to +1. Alright, my scale is just a quarter, just so I can have some dots down there to kind of know where I am on the graph. And then my y-min, I went from 0 to 3,500 just so I'd have enough room to see the intersection. Okay, I'm going to make my y scale 500 and then graph it. So there's the 3,000, and then here comes that function that, again, it grows extremely fast, and there's our intersection. So we want to find that intersection. So option 5 is intersect. Here's our first curve, that's the y equals 3,000. Our second curve, that's the exponential that we're looking for, and our guess somewhere around there. That's about as close as we can get. Alright, and then there's that 0.325 number that we saw again. Okay, so this is accurate. Okay, you can do this bringing in the logs to get rid of an exponential base, right, and then brings that t that was in the exponent down to where it's now just multiplication. So this is how we're going to get exponents that are the variable down on the same level with the other numbers to where we're able to solve for them. Alright, one big application of this is carbon dating and just other radioactive dating techniques. So this particular problem, they give us this decay rate, right, for this carbon-14, and the y0 represents the original amount of carbon-14 that was there, and y represents the amount of carbon-14 that's there t years later, or at present time, if y0 was years ago. Alright, so what this is saying is, if we started off with 1,000 grams, that's our y0, that's our original amount, right? The naught means like at times 0. Right, and then we went all the way down to 1 gram, and this is our equation, right? Y is the amount that's present there now. This was the original amount. So we want to find the age of the fossil. Alright, so we're going to do part A. We're going to set this up and solve it. So the first thing I want to do again is isolate the exponential part. So the exponential part, the part that has the variable exponent, is this. So we want to get this by itself. So the way we're going to do that, the way we're going to start, is to divide both sides by 1,000 to get rid of that 1,000. Alright, so I get 1 over 1,000, or 1,000th, is equal to e to the negative 0.0001297 t. Alright, so what, just like with the last problem, we have to ask ourselves, what undoes when the base is e? Now, in the last problem, the base was 10, and we brought in the common log, or the base 10 log, because that's what gets rid of a base 10. They wipe each other out. So what we're having to ask ourselves now is what gets rid of the natural base, e. Well, that's the job of the natural log, right? The natural log of e to anything, a, is just a. Right? Just like before, they wipe each other out, and that variable pops down. So that's what we're doing here. We want to use that property to get rid of this e and bring this t down on its own. So what we're going to do is we're going to bring in the logs. This is what I'm talking about, that step where I call bring in the logs. We're going to take the natural log of what was there before. And this is using the exact same logic as it was before in the last example. If these two things, this e and all this stuff, and this 0.001, if they were equal to begin with, and they were at this last step, then they're going to produce the exact same thing if we put them into the natural log. Alright, now, just like before in the last problem, the natural log and the e wipe each other out, and we're left with just this negative decimal. And that's equal to natural log of 0.001. Alright, last step, divide away the negative 0.000120097 from both sides. You may be wondering, why do they have such a long decimal? Well, we showed in class that the more decimal places you get, the more accurate you are. And we're talking about ages of fossils. We want to be as precise as we can with those decimals. So that's why we're getting such a insanely long decimal there. Alright, now our answer here exactly is this. Right? But as you might expect, if you ask somebody, how old are you, and they said, I'm the natural log of 1,000th divided by negative 0.000120097, alright, you wouldn't have any idea how old they are. So we go to our calculator to get a good approximation of that. So type in exactly what you see there in the home screen, the natural log 0.001 divided by negative 0.000120097. Enter. This thing is about 57,103 years old. Alright, and then find the age of the fossil using graphical methods. So again, that goes back to this original equation. Left side of the equation is 1. Right side of the equation is 1,000. E to the x button, if we have e to a power. Right, negative 0.12301297, and then just use x instead of the t. Alright, now t is about 57,000 years. Okay, so we're going to have to go way, way, way out to the right, so we're going to have to change our window. Alright, and I've changed my window to 0 to 70,000. Even though the number we're looking for is only about 57,000, I still like to go beyond it so we can see the intersection. Alright, I made my x scale 10,000 just to not have so many dashes on the scale. Alright, and then I made my y min negative 5 just again because I want to go below the intersection. The intersection we're looking for is where it crosses y equals 1. And then I made my x max 20 just because this thing's going to be coming down pretty steep on its descent down to that x-axis. So here's the graph of it. So there's the y equals 1 line, and here's that 1,000 e to the negative decimal. Alright, so we're looking for that intersection there. So that's second trace, option 5, intersect. Alright, first curve, that's my horizontal. So hit enter. Second curve, that's my exponential. Hit enter, and it looks like it's somewhere around in that area. Alright, so 57,103.044. So again, we're just validating that that answer is correct. Alright, the change of base formula, one of the most important properties of logarithms is we can change the base. So I know this may look all Chinese to you right now, but what this is saying is if we're given a logarithm with any base, a, we can change that to any base we want to using this property. Now look what happens. A was the original base. Alright, x was the original input into the original log. Alright, and look what happens. B is our new base. Alright, and then look what we have up top. The original input, the original base. Okay, so what that means is I can take any logarithm, alright, that I don't know how to put in my calculator because I don't have a log base 8 button, and I can change it into, in particular, what this is showing us, base 10 and base e, the common log, which we do have a button on our calculator for. There it is, right? And the base e log, which is the natural log, right? And that's what this is saying. So we can change any base into something that we do have on our calculators. So according to the change of base formula, this is like the a, right? This is like the x. Okay, a and x up here. So x was 124, a was 8. So I'm going to say that this is equal to the log of 124 divided by the log of 8. Right, and it's approximate. Throw that into your calculator. Log 124 divided by log of 8. Close those parentheses, hit enter, 2.318. Alright, and notice this says that you can use log or natural log. Notice if I use natural log, 124 divided by the natural log of 8, alright, I get the exact same thing. Alright, so it'll work with either of those log buttons, but we can transform any log function that we're given to the common log and the natural log using this formula. This is a really important formula, so make sure you take the time to pause the video and write these down because you're going to need these in your homework and then the tests in the future. Alright, investments. So this is a function that tells us how much an investment is worth T years after this $10,000 was deposited in this account that pays 10% compounded annually. So we want to know how many years will it take for the investment to get to. Alright, so we're going to set that's our S. So we're going to put 45,950 equal to 10,000 times 1.10 to the t power. Alright, so basically all we've done here is just replaced S with what this thing tells us that it needs to be. Alright, now just like before, here's our exponential part that we want to isolate. So we're going to divide away this 10,000 on both sides. Now, obviously what happens on the right is it just goes away, but remember on the left, a little shortcut, if you remember, when you divide away by a power of 10, which means a 1 with a bunch of zeros after it, for every zero there's 4 zeros. Put a decimal at the end of the number and count back 4 places. 1, 2, 3, 4. So 4.5950 equals 1.10 to the t power. Alright, no need for the parentheses anymore. Now, here, if we're going to use this most recent property we talked about, the change of base, we're going to bring in, this is where we bring in the logs. Once we have that thing isolated, we bring in the logs. Now, what log base am I going to bring in? I'm going to bring in the log base 1.10. 4.5950 equals the log base 1.10 of 1.10 to the t power. Now why would I do that? Because again, I want this stuff on the right hand side to cancel out, so I just left with that t power. And just like we've been doing, if this base down here is the same as this base, this logarithm and this exponential wipe each other out. So we're going to get rid of this 1.10 and this whole log, and that t is just going to drop down. Alright, so what are we left with after that step? We're left with the log of 1.10 of all this stuff, 4.5950, equals t. And there's our answer. Okay, we're solving for t, right? So there it is. Now, that's ugly. That's horrible. How can I come up with that? Well, let's change a base. If you have the log base anything of some input, then we can change it to the log of the original input divided by the log of the original base. So all this is equal to, according to the change of base, t is equal to the natural log of the original input, 4.5950 over the natural log of the original base, 1.10. Alright, go to our calculator. Alright, natural log of 4.5950 divided by natural log of 1.10. Alright, and our answer is about 16 years. Alright, so this does come in handy when we're solving some of these formulas if we have a base that's not a common base, like a base 10 or a natural log, like an e base in there.